Now, vertical stretching and shrinking. Let's take a look at how the parent graph is actually modified in this case. So if we're playing again with the parent graph, we always kind of define the parent graph as f of x. There's always going to be some constant multiplied to the outside of this parent graph. That's where we see that c from. And so if you guys remember the whole movement, if f of x always means the same thing as y, well, that c value is multiplied to the y, which means the y values are going to change. So this will help us as we're going through this. Now, it depends what the number you're multiplying is. So you want to pay attention to whether or not the number is a fraction in between 0 and 1, or if it's a number that's greater than 1. So what we're looking at, in both cases, there's multiplication happening. You could actually do the math on the y values, and that might make it a little more clearer. Or you could kind of use your TI to tell whether or not you're vertically stretching or vertically shrinking. So if we wanted to do that together, we can do this. We could say, well, what happens if our trusty TI, and we can say, hey, what if the parent graph was square root of x, and we want to have a new function, g of x equals, let's see, c is greater than 1, so let's pick like 2 times square root of x. Well, what it's essentially doing is it's multiplying every single y value by 2. And you kind of know if you multiply every y value by 2, you tend to make it larger. And so that would vertically stretch it. If you're not quite convinced, we just pull out the TI and we'll go from there. And let's erase our previous y2. So we have our parent graph. This time I'm going to say 2 times square root of x. Now if we graph, notice that the graph, it didn't shift, it just moved, it multiplied every single y value by 2, which makes those y values grow or stretch. So there's no movement going on, it's a stretch. The other case I want to look at, let me switch back really quick. If we were to consider, what if our g of x was involving a factor that was in between 0 and 1, so nice fraction or decimal. I'll say 1/2 times square root of x. What's supposed to happen is it's supposed to shrink vertically. And if you think about what happens when you multiply a number by something that's smaller than 1, it's supposed to make the number smaller, as long as it's in this sort of range, 0 and 1. So if we kind of, we can guess what's going to happen, but you could also use your TI to further verify for yourself. So we can do that. Go back to the y equals. And if you'd like to, if we're going to write a 1/2, I'm a little paranoid, so I'll use the 1/2 in parentheses so the calculator doesn't get confused. I have 1/2 being multiplied by square root of x. I think you could also use the decimal equivalent if there's a nice concrete terminating decimal. So a number 1/2, like if you say what's 10 and half of 10 should be 5, it's going to make the number smaller. So if we graph it, it should see that the parent graph, which was blue, compared to the new graph, which is red, we're seeing that the y values have shrunk vertically by a factor of 1/2. And we can explore this a little bit more. I like to do this with the abstract example that we see right here. So let's do that together. And I want to point out to you that when you do look at your function that you're trying to modify, g of x equals 1/2 f of x, it's also You could write it as 1/2 times y if you're kind of thinking about what's happening. So the y values are all going to get multiplied by 1/2. Now, I could kind of show you a couple ways. I'm going to do like an ordered pair approach, but if you know how fractions work and you know how to have things, you're cutting the y value in half. So sometimes you can visually do this too. But I'll write in English what's actually happening. Because I see this 1/2, f of x, we are going to be shrinking vertically by a factor of 1/2. And what that really means is every y value are multiplied, or will be multiplied by, you guessed it, 1/2. So sometimes if you're having a hard time getting these shrinking and stretching vertically problems, I may go with the ordered pairs. So if you see me look at the graph of f of x, I'll write it onto the right for you all. F of x, if I make an XY chart, if I'm looking at each ordered pair, I do have the first one on the left, -4, -1. The second point, -1, -2. The third point, 2, 3. And the fourth point, 4, 1. So just so that you know, I just named the coordinates of each of these points. And so that's who my f of x is. Now, if I'm looking at what I want to happen, I need to understand that g of x is 1/2 times f of x. So I actually can draw another column, and I'm looking at what is 1/2 multiplied by f of x. And so what it does is it takes each of these y values and it multiplies them by 1/2. Sometimes easier said than done. Did I miss one? Yeah, there we go. So sometimes it's easier to visualize it. Sometimes it's easier to do the math. Everyone's different. So I try to present both ways so that you guys have options. So if we do that, and we're going to say, okay, what is 1/2 times -1? And that should be, for us, should be -1/2. What is 1/2 times -2? That should be -1. What is 1/2 times 3? We can say 3/2. Write that in. And what is 1/2 times 1? It's positive 1/2. So you essentially have the ordered pairs of your new graph in this coordinate approach. We can draw those in automatically. So I'd be graphing, the x values have not changed. So -4, -1/2, we would see, okay, should be somewhere in between. -1, -1, our new point. 2, 3/2. And just remember, sometimes 3/2 is not friendly. That's really like saying 1 1/2. So 2, 1 1/2. That's about right here. And the last one, 4, 1/2. We can draw that in. And we end up having our function, which, notice the x values have not changed. It's the y values that got compressed. So they were shrunk vertically by a factor of 1/2. So that sometimes people like to do it this way because they have a clear idea of what the actual coordinates will be. Other people kind of have a visual approach. So, you know, sometimes you have a strength in one or the other. I'll show you the visual approach, and sometimes it involves me drawing it on the same graph. And what I try to understand for myself is when I'm looking at each of the points, depending on what this factor is, in our case, it's a positive 1/2, you are multiplying each of those y values by 1/2. In other words, you're cutting the distance from that point to the x-axis in half. So if we kind of see this first point, the distance from the point to the x-axis, and we're going to cut that in half, that ends up being right here. And similarly, the distance from the second point to the x-axis, it's 2 units at the moment, but if you cut 2 units in half, that means we have the point ending up being at -1, -1. And if we look at the distance from the third point to the x-axis, if you cut it in half, the cutoff would be right here. So we have that third point. And the distance from the fourth point to the x-axis, if you were to cut that distance in half, then you would have the next point. And so this is going to also give you an accurate graph. If you connect the line segments, do yourself a favor and get a straight edge. That translates to g of x. So sometimes, some of you, it might be easier to cut distances with the idea of what it means to be a fraction. Some fractions are easier than others, like half is very friendly. Maybe 1/4, maybe 1/3 is very friendly, but sometimes when it starts to range into like the 5/6, that might be a case where we promote maybe going to the coordinate method. But kind of play around, see what works for you. Practice, practice, practice. And I'll see you next time.